Hey, it's Horner. We're going to look at 16.6. This is conductors in electrostatic equilibrium. Materials that tend to pick up charge easily are conductors, and it's because they have charges that move around really easily. And so when we think about equilibrium, or what we're going to call electrostatic equilibrium, we're mainly thinking about conductors. So for example, if I have a Van de Graaff generator, that's that thing with the silver ball on the top that if you put your hand on it, your hair stands up. Because it's metal, those charges can move around pretty quickly. But once those charges kind of settle out, we call that electrostatic equilibrium. So that's mainly what this section is about. If a charge is put on one of those conductors, those little charges will move around until they're all pretty equally spaced out. And we can apply an external field to it. And when we do that, all those charges will move. But then when we kind of leave that field where it is or take that field away, all those charges will give us this equilibrium distribution again. And so there's some important things we need to recognize about conductors and electrostatic equilibrium. The first one is the electric field is zero at any point within a conducting material in electrostatic equilibrium. So if I have a conductor in electrostatic equilibrium, only the surface can have a charge. So let's go back to our Van de Graaff generator. That ball on top, there won't be any charges on the inside. The only place that we'll see charges, either positive or negative charges, will be on the outside surface. So point 3 here says the electric field at the surface of the conductor is perpendicular. So the field here really should be perpendicular to the surface like this. A non-perpendicular field would not be an electrostatic equilibrium. So we really want these to be in equilibrium. And if that's true, then the electric field at that surface should be perpendicular to it. And then finally, the surface charge density. So all that means is that where the charges are on a conductor in equilibrium is really high at the sharper points, and it's really low at the more blunt points. So you'll notice that we have a lot of charges here just right at the tip of the conductor, and then back here in the more flat part where there's not a lot of sharp points. We're not thinking about this or this. This is just a cutaway. You'll see that they're a lot further apart. So that'll be important in some of our discussions. For a conductor in electrostatic equilibrium, there's no field lines within that conducting material. So remember we said that that Van de Graaff generator would have all of the charges on the outside, and because of that you're not going to have any electric field lines within that conducting material. Field lines that start or stop on the surface are perpendicular, so the field lines here are going to go straight away because these are all positive charges. And the electric field just outside the surface is strongest near the sharp point. So if this for some reason was bent and had a sharp point on it, for example, let's just take right here and let's make a sharp point right there. We would have a lot of positive charges right here. And then we wouldn't have as many on this flatter part, well, not flat part, but on this more symmetrical curve part where there's not a lot of sharp points. So those are 7 important points to know about conductors in electrostatic equilibrium. Next thing here is example 1611, and it says a solid conducting sphere carries a total charge of negative 16 microcoulombs, and it's placed at the center of a hollow conducting material shell that carries a total charge of positive 8 microcoulombs. The conductors here are in electrostatic equilibrium. So they want us to determine the charge on the outer and inner surfaces of the shell and sketch a field line diagram. So now we can apply any of the conclusions we just reached about conductors as well as the properties about their field lines and see how those work out. So here is the field lines outside the solid sphere. Notice that they're all pointing towards the middle of the sphere. They are equally spaced on the outside, but the density is higher near the surface than it is way outside. If we're inside a shell, okay, so if there's a shell surrounding it, you'll notice that we have field lines starting at the inside of the shell and then moving towards that conductor. If I have a complete field line sketch, now we've got both objects. We've got the field lines coming in. Notice how they're further out. And then we've got these other field lines that are on the inside. So we need to go back and take a look again at the numbers that they gave us. So if we go back and take a look at the numbers, we see that the solid sphere has a charge of negative 16 and we see that the hollow conducting sphere shell is +8. So there's a much bigger charge on the inside than there is on the outside piece. So the outside piece, here are those charges. This one's positive. So we've got things emanating from here and moving on into the inside of that shell. Conductors in electrostatic equilibrium, lightning rods are really important. Lightning rods, there's a little bit of dispute as to how they work, but basically it's a sharp tip piece of metal. Those are typically then on top of a building, and then they would go down into the ground. So there's actually a wire that would connect down to the ground. And the hope is that the bottom of a cloud, let's say that it's negative, if this is a positively charged rod, that we will get a little bit of that charge leaking down into the lightning rod itself, so that if there is a strike, it's on the rod itself and not on the wooden part of the structure, just to kind of prevent some of that fire safety. The next thing that you see here is called an electrostatic precipitator, and basically what it is just a dust collector. So you'll see these in a lot of homes have the electric air cleaners, and basically what happens is we've got positive and negative plates. There's an electric field there, and the dust actually collects on the negative plates. So the dust is positive, it sticks to the negative plates, and then every once in a while you have to clean these plates. So let's go ahead and take a look at QuickCheck 20.23. We have two parallel plates. Here's our parallel plates. They have charges of equal magnitude but opposite sign, and they want to know what change could be made to increase the field strength between the plates. So we want to increase the number of lines between the plates. One thing that I tell students is you can always know the number of field lines and the field strength by just connecting these two. So the number of charges here will do that. So that's one way to look at it. So we can increase the magnitude of the charge on both plates. Here it says decrease the magnitude of the charge on both plates, increase the distance, decrease the distance, or increase the area of the plates. So our answer here, of course, is we can increase the number of charges. If we do anything else, it won't do that. All we want to do is just put more positive and negative charges. So if we put more positive and negative charges, so I'm going to add some here. Oops, that's negative. This one's positive here. I'm going to add more field lines, and that's how you do it. Increasing and decreasing the distance doesn't do anything in terms of the field strength. It just puts a bigger separation between the plates. That's 20.23. 20.24, we have two plates of parallel plate capacitor, have charges of plus Q and negative Q placed on them, leading to a uniform electric field. The distance between the plates is doubled, so the electric field, remember we said that changing the distance won't do anything. It just, it's the number of charges that are on those plates, so it just remains the same. For 20.25, a set of electric field lines is directed as shown. At which points of the noted points is the magnitude of the field the greatest? So wherever the field lines are really close together, that's where our electric field is going to be really big. So A is going to be the biggest field strength here, and so we'll see that that one is checked. We have two protons. Here's A and B. They want to know which proton has a larger acceleration. So we've got to see which one has the strongest amount of field strength acting on it. And we notice that it is A because the lines are a little bit closer together. And where the field lines are further apart, the field just isn't as strong. So it wouldn't have as much of an acceleration out here as it does at the very beginning. For 20.27, it says which of the following is the correct representation of the electric field created by the two positive charges. And remember, we always have field lines going away from the positive charge. So this one you've got going from and to, so that one can't be right. This one, of course, can't be right. Here we see they're separated, but this one, the charges are, the field lines are coming towards, which is not right. Here they're going away, and they're going away for both. So our answer here has got to be C. This is 20.28, and it says an electron is in the plane that bisects a dipole. What is the direction of the electric force on the electron? So Here we've got our electron bisecting the dipole, so it's right between the two. And the force should be away from the negative charge and towards the positive charge. So it should be in the direction that we have labeled here as A. This picture kind of shows it a little bit better because they're separated a little bit better, but the force is actually going to be in the opposite direction of the field. The field points down, but because it's an electron, it's going to move anti-parallel to that field or move up. And that is the end of this section.